Hello everyone and welcome to our talk. My name is Nicola Romaro and today I will present our paper, SYML, Guiding Symbolic Execution Toward Vulnerable States Through Pattern Learning, which presents a novel path prioritization technique for dynamic symbolic execution that uses machine learning to direct the execution towards states that are more likely to be vulnerable. Since the main focus of our work is dynamic symbolic execution, we will start off introducing this concept. Dynamic symbolic execution is a promising approach for vulnerability discovery that, because of its versatility, has gained much popularity in our community in the last few years. Dynamic symbolic execution has a variety of applications, and as you can see, and as you can already judge from its name, it comes from the combination of two different analysis techniques: dynamic analysis and symbolic analysis. First, as opposed to static analysis, which create an offline model of the application and then apply heuristics or formal methods to find a potential vulnerability, dynamic analysis instead can execute the entire application instruction by instruction in an emulated environment, and therefore they can reason about the execution path that was taken and that needs to be followed again in order to trigger the vulnerability or error that was just observed. This additional knowledge about the execution path means that dynamic analysis will only report vulnerabilities that are verified and replayable. Similarly, while concrete analysis will execute the program with a concrete input and cannot reason semantically about the program itself, symbolic analysis can execute the program in the abstract domain of symbolic variables. So, as you can see in the example, symbolic analysis will fork the execution after every conditional instruction and will generate a constraint that mirrors the branch condition. In the example, in order to reach the error state, the symbolic execution engine will accumulate the constraints x equal to z after the first if instruction and x greater than y plus 10 after the second if instruction. This allows symbolic execution to understand what symbolic variables are associated with each of the conditional instructions, and therefore determine the specific portions or specific bytes of the input that are responsible for certain program behaviors, such as the error state in this example. So, in summary, dynamic symbolic execution is a program analysis technique that executes the program in an emulated environment and in the abstract domain of symbolic variables, thus providing both replayability and semantic insight. Dynamic symbolic execution has a variety of applications, such as program verification, exploit generation, deobfuscation of obfuscated software. However, what we will focus on in this presentation are mainly its applications to vulnerability analysis. The problem with dynamic symbolic execution is that since the execution is forked after every conditional instruction, as we have discussed during the symbolic execution example, the number of branches will grow exponentially with the number of conditional nodes. As a result, after exploring n conditional nodes, we will have forked, in the general case, 2 to the power of n execution paths. But our time and resources are limited, and we cannot afford to explore exhaustively the whole program. So, for this reason, we will have to limit our exploration to only a selected subset of the execution paths. There have been many attempts to mitigate the problem of path explosion. For example, symbolic-assisted fuzzing combines fuzzing and symbolic execution using the symbolic execution engine to reason on the blocking branch conditions only when the fuzzer component gets stuck. Under-constrained symbolic execution allows to execute only parts of the target application, giving up the replayability of the bugs that are detected in exchange for scalability. Merging execution paths can over-approximate and merge different states in the symbolic execution engine, while interleaved symbolic execution can bring a human analyst in the loop in order to combine concrete analysis with symbolic analysis. Finally, path prioritization is what we will focus on in this presentation, and consists in choosing the best subset of execution paths while maintaining a pure symbolic execution approach. Path prioritization techniques are classified as either classic tree traversal or heuristic-based. We all know the classic tree traversal algorithms such as depth-first search, breadth-first search, etc., and heuristic-based techniques such as CLE's coverage optimization or AEG's loop exhaustion are techniques that make use of specific metrics such as coverage or loop iterations in order to score and prioritize paths. For example, the loop exhaustion heuristic executes a loop over and over again and can therefore trigger simple buffer overflows or memory corruption bugs. Coverage optimization instead attempts to select states that are likely to cover new code in the immediate future by maximizing some heuristics, and it is therefore more likely to find errors that derive from a poor testing of the target application. The problem with all these path prioritization techniques is that they are not necessarily targeted at vulnerability discovery, and their analyses are often shallow and vulnerability specific. Our approach builds on the idea that more coverage does not necessarily mean more bugs. Instead, what we want to do is to replicate the expertise of a human analyst that can easily find and that can easily point at some interesting patterns just by looking at a snippet of code. The core intuition of our approach is that similar bugs often result in similar execution patterns, such as sequences of API calls or system calls, executions of complex functions, etc. And so we can leverage this information to find interesting execution contexts in a target program. This allows us, for example, to get around the uninteresting functions that cause path explosion and instead focus on and get right to the point where the vulnerability happens. Our approach is structured in 4 stages: concrete tracing, dynamic symbolic tracing, training, and prioritization. You can see the diagram here on the right side of the slide how these 4 stages interact, from the concrete tracing of the binaries and question inputs to the prioritization stage, where we use our prioritization strategy to predict vulnerable states in unseen programs. The dynamic symbolic execution framework that we use is the UNGER framework, which is a very popular open-source binary analysis framework that is developed and maintained at UC Santa Barbara and Arizona State University. We use the UNGER framework in 2 stages, the dynamic symbolic tracing stage and the prioritization stage, as you can see from the slides. Our first stage is the concrete tracing stage. The concrete tracing stage is where we run concretely our set of binaries and question inputs in the QEMU emulator. We then monitor the execution of these binaries and collect the execution traces that correspond to each one of the question inputs. During the second stage, symbolic tracing, we initially run some static analysis to extract symbols, contour flow graph, function information, etc. We then load and execute the binary in the UNGER framework and synchronize the execution with the trace that we previously recorded during the concrete tracing stage. After every conditional instruction, the execution will fork, and we will create 2 new training points in our dataset, one for the taken branch and one for the missed branch. For both the training points, we extract features that capture the current execution context, For example, we extract historical information, such as the number of branch visits, local information that summarize the short-term behavior of the branch, such as the centrality of a node, function size, function complexity, etc., and finally, forward information that summarize the long-term behavior of the branch, such as system calls, register operations, memory accesses, etc. Our third stage is the training stage. During the training stage, we will clean the dataset and prepare the numerical and categorical features extracted in the previous stages. We will then train a set of models or classifiers that will learn to predict the outcome of the branch prediction based on these features. For example, we train a logistic regression classifiers, a decision tree classifier, a random forest classifier, etc. We use a leave one out cross-validation to validate our model, training on n-1 binaries at a time, and testing on the single binary that is left out. We will now go through an example to make these first three stages clear. During the concrete tracing stage, we will start our analysis with a set of vulnerable binaries from our dataset. We will execute these binaries concretely in the QEMU emulator. We will monitor the execution and feed the emulator with the crashing inputs. At this point, as a result, we will record all the basic blocks that are executed during the execution of the vulnerable binary, which we call the execution trace. The symbolic tracing stage will take as an input the recorded execution traces. It will then load and execute the vulnerable binary or the vulnerable binaries in the Anger framework. It will extract static information such as the control flow graph, function information, and other metrics that describe the program structure. And will create two new training points when forking the execution after every conditional branch, extracting historical information, local information, and forward information. At the end of the symbolic tracing stage, we will have a complete dataset of branch outcomes, such as taken and not taken, with the associated features for every branch executed in the vulnerable programs. So during the training stage, we will take this dataset as an input, pre-process and prepare the numerical and categorical features, and finally, train our classifiers. As discussed earlier, we train many different models. To evaluate our classifiers, we will train the models on n-1 binaries at a time, use the branches in the nth binary as our testing set, use metrics such as accuracy, coverage, and time to score to measure the performance of the classifiers, and then repeat this process for n folds. In this example, we assume that the model with the best performance is the XGBoost model. The fourth and last stage in our approach is the prioritization stage. During the prioritization stage, we execute and explore unseen binaries from our dataset. This stage is very similar to the symbolic tracing stage that we have described before. However, instead of following a recorded execution trace, we use the trained classifiers and a prioritization strategy to direct symbolic execution towards states that are more likely to be vulnerable. After every conditional instruction, first, we use the XGBoost classifier to score all the execution paths in the symbolic execution engine. Since the predictions are not perfect, and the search space is often large, we want to make the best possible use of these prediction scores. We then use two prioritization strategies to decide which path to prioritize given their set of scores. The fast strategy will just treat score as an absolute value and always prioritize the path with the maximum score. However, paths are often very similar, and having more than one promising path is possible. For this reason, the balance strategy considers scores as a probability measure instead of an absolute value, making the strategy more resilient to errors. In order to evaluate our approach, we first implemented prioritization techniques from the state-of-the-art in a unified framework, Anger. Our initial dataset is composed of binaries and crashing inputs from the Cyber Grand Challenge dataset, as well as 3 real-world CVEs affecting Linux binaries that we use to show that transferring knowledge from the Cyber Grand Challenge dataset to a Linux x86 setting is possible. Finally, we run every binary on one CPU core. We monitor the analysis for 24 hours and check and classify the resulting crashes. The Cyber Grand Challenge dataset is a very popular dataset composed of statically compiled x86 binaries with known vulnerabilities, and crashing inputs to trigger these vulnerabilities. Cyber Grand Challenge binaries have semantics that are similar or that are equivalent to Linux binaries, but run on the Decree operating system, which is a slightly different operating system with a smaller set of system calls. In our experiments, we also use 3 Linux CVEs from the programs ASP2PHP, O3Read, and Ringtone tools. To evaluate our approach, first, we need to choose the best classifier to predict vulnerable branches. In this table you can see the performance metrics of all our classifiers after the cross-validation on the Cyber Grand Challenge dataset. As you can see, the 3 most promising classifiers are the Random Forest classifier, the AdaBoost classifier, and the XGBoost classifier. However, considering that we will have to use this classifier in the context of symbolic execution engine, performance are particularly important. So considering the performance constraints, we will choose the best performing model, which also has to be simple and fast. This leads us to choose the XGBoost model over the Random Forest and AdaBoost models. The accuracy and F1 measures of the 3 models are comparable. However, the XGBoost model has both a better time to score and a higher coverage, where the coverage or trace coverage is a metric that we use to measure how many distinct branches the classifier can predict correctly. We then explore every binary in Cyber Grand Challenge dataset, using our XGBoost classifier to predict vulnerable paths and direct the symbolic execution toward these interesting paths. When running and monitoring the analysis for 24 hours, the results that we observe are presented in slides. You can see how, starting from the bottom, the technique that triggers the lowest number of crashes is CLE-random, which is a slight variation of a purely random heuristic. This is followed by the coverage optimization heuristic, the loop exhaustion heuristic, and finally SyML. It is interesting to note how SyML finds more vulnerability than any other approach, as well as some vulnerabilities that are not found by any other approach. We then analyze the feature importance measures for our classifiers and the distribution of the prediction scores during the exploration. We analyze and compare the features importance for the XGBoost model and the Random Forest model, showing that some features, such as the number of branch visits and whether the branch is leaving the current connected component, are important or are more important than others for the classifier's predictions. Similarly, we analyze the distribution of the prediction scores during the exploration of a vulnerable binary. The figure in the slide presents the score distribution over time, showing how scores increase as SyML gets closer to the crash and drop immediately after the crash when the exploration starts exploring different and less interesting paths. Finally, we show that it is possible to transfer knowledge from the Cyber1 Challenge dataset to explore Linux x86 binaries. In fact, dynamic symbolic execution inaccuracy makes it hard to retrace Linux binaries and build a large dataset of Linux x86 binaries. However, Cyber1 Challenge semantics are analogous to the Linux x86 semantics, and this allows us to transfer some of the knowledge that we have learned from this larger Cyber1 Challenge dataset to the smaller dataset of Linux binaries. As you can see from the table, when we train the XGBoost classifier to learn patterns in the combined CCC plus Linux dataset, we obtain a much better result than when the classifier is trained only on the Linux dataset or only on the Cyber1 Challenge dataset. As a conclusion, in this line of research, we propose a novel prioritization approach that leverages supervised learning to direct dynamic symbolic execution and reach interesting and vulnerable paths. We evaluate our approach on the Cyber1 Challenge dataset, showing that it outperforms prior work in path prioritization. And finally, we effectively transfer the models that we learned on the Cyber1 Challenge dataset to achieve a better prediction accuracy on 3 real-world CVEs affecting Linux. As a future work, we believe that it would be interesting to train SyML on a large dataset of Linux binaries, using a different retracing framework to allow scaling to Linux x86. It would also be interesting to adapt and apply this approach to guide a hybrid fuzzing engine, which could be, in general, more performant than a pure dynamic symbolic execution engine. Thank you everyone for your attention. I would also like to thank all the people that contributed to this research, without whom this work would not have been possible, and extend all of our gratitude to the RIDE organizing committee and program committee. Please feel free to ask any questions or to reach out at the email that I indicated here in the slide. Thank you.